This video is the second of two devoted to the definition and the exhibition of examples of tempered distribution. Let us recall briefly the definition of the space S of R, which is a space of smooth function on R, such as all the derivatives decay faster than any power of x, and this behavior is described by norms like this. Ns of index n means that all the derivatives less than order n decay faster than x to the power minus n at infinity. Okay, and tempered distribution is simply a linear form in the space S which has some continuity property for one norm of on S, and doesn't matter the index n, some n exists, that's important. And we denote this space by S prime. This is space, the set of tempered distribution. So the example we have in mind are really quite far away from functions, and the first one, this is the following, that observe first that the map that x associated this ratio is integrable, and the linear form defined by this integral is a tempered distribution. Okay, let's prove this. So the fundamental inequality of a calculus claims that this difference is less than 2 times the absolute value of x times the supremum of the derivative of phi. And of course, because phi is in S, this function decays faster than 1 plus x at infinity. Okay, so both information gives that for x less than 1, this ratio is bounded by 2 times the norm of order 1 on S, and for x bigger than 1, this ratio is bounded at 2 times of x squared times the norm of index 1 on S. So, of course, this function is integrable, and when you integrate the function, you find the wanted inequality. So this proves that Vp of x, we call the principal value of 1 over x, is a tempered distribution. And why one interest of this distribution is the following. Consider a function phi in S which vanishes near 0. Then the absolute value of 1 of x, which is here 1/2, you can write it like this, phi x of x divided by x. Both are integrable. Okay? And here, changing variables x in minus x here, it gives you the wanted formula. What does it mean? It means that, in fact, if we look outside 0, this distribution principal value of 1 over x acts exactly as 1 over x. 1 over x is not a function on R because it's not locally integrable on R, but outside 0, of course, it's a locally integrable function. So, in some sense, the principal value is a sort of extension of 1 over x over all R, and not as a function, but as a tempered distribution. Let us see another example of this. So again, this ratio here is an integrable function, and the finite part of 1 over x squared defined by this integral is a tempered distribution. Okay? Let's prove this. So Taylor inequality, because the derivatives of this function at 0 is 0, Taylor inequality at order 2 ensures exactly this. Voila. Now, let us go outside 0. Now we use simply that this is bounded, and this is 1 over x squared. So we have this. Okay? So this function is integrable. So this function is integrable, and we integrate this function. We find the wanted inequality, and it ensures that Pf squared is a tempered distribution. Well, now we are going to make the following remarks, that if phi vanishes near 0, we can, of course, this term does not appear, and again changing variable x into minus x, it turns out that the principal value of 1 over x squared is equal to the integral of phi x divided by x squared. So outside 0, this distribution finite part of 1 over x squared, it acts exactly as 1 over x squared as a function. Again, 1 over x squared is not a function on R because it's not locally integrable in R. So in some sense we have extended 1 over x squared not as a function but as a distribution. And to conclude this series of examples, let us show a distribution has a limit of a sequence of distribution. And what a limit of sequence of distribution, we define it like this. This is in fact the weak star convergence. In fact, it means that a sequence of tempered distribution converges to a tempered distribution in and only if we test this distribution, the sequence on a given test function, the limit of this is t applied to phi. And we are going to give an example that the sequence made by the sum of the n first function sinus nx, this converges in S prime to some distribution we are going to define. Okay. So we have to find a distribution S such that for any function phi in S, we have this converges. And using integration by part, we have this. So the detail of this is an exercise you can do by yourself. Once we have this, we see here we have some decay. So let us define this function phi sigma of x. This is the sum for n equal 1 to infinity of 1 over n squared sinus nx. This belongs to, this is a continuous bounded function on R because it's a normally convergent series. Okay? So now let us see what's going on. In fact, if we can define this function as a distribution, why this is a distribution? Because this is bounded. This decay faster than x squared at infinity, so this is integrable. And of course, here, if I put absolute value here, I have this is less than some constant, which is the supremum of sigma, times the norm of in this 2 of S, simply to ensure integrability. Okay. So this proves that this is a distribution. So now we are going to see the convergence. Why do we have this? Simply because what we saw already is that this is minus sum n equal to 1 to infinity of the integral of 1 over n squared sinus nx phi second of x dx. And this sum here, put the sum inside, and this is normally convergent. This is uniformly convergent to sigma. And then you pass to the limit in the integral and you find the result. So here, the limit of this sum, we have proved that the limit of the sum of nx, this is a tempered distribution that associated the integral of sigma x, the second derivative of phi. And this concludes the series of examples of tempered distributions.